Greetings and welcome, friends, boys and girls of all ages, math lovers, math haters. Hey, it's okay. Here we go. We're gonna learn some math. I'll learn some math at you. We're on page 166. We were talking specifically about continuity yesterday, and here's question 14. It says, determine whether each function is continuous at the given x value. Justify your answer using the continuity test. Big hint right there. It's a three-part test you should be familiar with. Now, I might actually be interested in a little bit in the graph of this, but let me just jump right in this and see what we could figure out first. Some of this you could figure out through some sort of table-type approach, really. The first part of the continuity test is, does f of c exist? So, for instance, does f of negative 3 exist is the question. So, negative 3 plus 3 all over negative 3 minus 3 all squared. Is this going to exist? I actually don't see any problems with this. The numerator is 0. The denominator would be negative 6 all squared. Oh, it looks like I'm getting a little bit of lag there. So 0/36, which is equal to 0. Right. So it does exist. So it passes part 1 of the continuity test.
Why would it not exist?
Well, for instance,
If the bottom was 0?
yes.
Okay.
If I plugged in positive 3 here, it would fail part 1 of the continuity test because 3 minus 3 is 0, 0 squared is 0, dividing by 0 is undefined. So yep, so that's part 1. Part 2 of the continuity test asks the question, is it approaching the same value from the left and the right of that point? Now, I could make a table of values. I could plug in something like negative 3.001 and negative 2.99 and figure out some numbers like that. I'm going to show this to you graphically here real quick. And let's take a look at this. So I've got x plus 3 divided by x minus 3 squared. Looks like I've got that plugged in right. And when I graph this, let's change the line color. We'll do a nice little dark purple. And, we'll change the thickness to medium there. So this is what I've got. Here's our little graph. That looks good enough to me. And so here's our graph. Now, I'm interested in the point negative 3. So question, my friends, let's see, here's negative 1, negative 2, negative 3 right here. We've already decided that it exists at that point. The question I'm asking now is, does it approach the same value from the left and the right? Those two arrows are pointing at each other. So yes, it does. What value does it appear to be approaching? It appears to be approaching 0, right? It appears to be approaching 0 from the left and the right. And then question 3, or part 3 rather, of the continuity test asks, is the number that it approaches from left and right the same as the number it actually is at that point? Yes. So this is continuous at x equals negative 3.
Because both the numbers are the same?
Yes.
So if they weren't the same, it wouldn't be continuous.
Correct. So, so using the same graph, we saw that if it had an empty hole here and say it like had the point jump up there, it would have existed at that value. It would have approached the same number from both sides, but the number it approached from both sides would not have been the same as the value it was at that point. So that's how it could have failed part 3, if you were wondering. Looking at the same graph, what about at x equals positive 3? Does it pass part 1 of the continuity test?
Yeah. No.
Here, let me just write this down here. I'll just say x equals 3. Let's do some 1, 2, 3s here real quick. Might as well for the practice. So does it exist there? No, so it fails that part. Does it approach the same value from the left and the right?
Yes.
Well, They both go to infinity, but that is not a y value. That is a concept and not a number. So no. And then does the number it approach from left and right, which it doesn't, is that the same number that it is at that point, which it doesn't exist at that point? 3 just fails by default. So x equals 3 is discontinuous at this point. All right. So just so you're clear on kind of how that continuity test works, friends. Here, let's take a look at 16 here. It says, so this is what's called a piecewise function. This is what we got here. I've got 3x plus 5, or the slope of 3, y-intercept of 5, whenever x is less than or equal to negative 4. And then whenever it's greater than negative 4, it is equal to negative x plus 2. So let me actually get some nice little graph paper here. Let me get some undos going here. Bam, that looks good. Let's see, is my graph going to fit? Yeah, I think it'll fit between, hopefully it does, between my 10s. Do the classic 10, 10, 10, 10. That sounds good. And let me get a nice little graph of this going here. So let's analyze this first part of the piecewise function. So 3x plus 5 if x is less than negative 4. So this will be kind of like my threshold here. This isn't an asymptote. I'm just kind of making a mental note to myself. 1, 2, 3, 4. Yeah. So right here, the graph is going to be one thing on the left and another thing on the right. All right. The fact that it is piecewise does not determine whether it's continuous or not yet. That just tells me 2 separate equations represent it.
What is piecewise?
It means it's like a series of pieces like chunked together. Like, so you could actually have like a parabola and a line and all sorts of stuff. So a series of graphs all chunked together to make one graph. So 3x plus 5. So the slope is 3, the y-intercept is 5. So if the graph existed over here, it would have been here. And then the slope is 3, so I could have gone up 1, up 2, up 3, over 1, right, like so. Or, let me get some other points, down 1, down 2, down 3, backwards 1, down 3, backwards 1. Let's see, hopefully I have space for this. Down 3, backwards 1, down 3, backwards 1. So here, it just came into existence. And then down 3, backwards 1. So it exists right here. These dots technically don't exist as part of that graph. I was just using that to try to graph this portion. Let's see the other piece of the graph. Let's graph this one in green. The slope is negative 1. The y-intercept is 2. Anytime x is greater than negative 4. So let's see. The y-intercept is 2. So right here. And the slope is negative 1. So down 1 over 1, down 1 over 1. And down 1 over 1. Here's some points. But let's actually, I'm interested in kind of what's happening over here. So let's go up 1, backwards 1, up 1, backwards 1, up 1, backwards 1, up 1, backwards 1. Now, would it be an open circle or closed circle here?
Open.
It's an open circle because this did not include the equal part here. So if I draw this, terrible, something like so. This is what my piecewise function looks like. So the point that it is right here is at negative 4, negative 7, and then it jumps. So this is, you might remember, is called a jump discontinuity. But let's actually analyze this using the continuity test, even though it might be obvious to you experts out there. First of all, part 1 of the continuity test, does it exist at x equals negative 4? Yeah, that's a go. That's good, right? It exists. It's right here. Bam, there it is. I just proved it to you. It's right there. It exists. Part 2, does it approach the same number from left and right? From the left, it's approaching 7. From the right, it's approaching, or sorry, negative 7. From the right, it's approaching positive 6. So it failed that part of the continuity test. And part 3 is the number that it approaches from left and right, which it doesn't. Is that the same as the number that it is at that point? No, that just fails by default. So the answer to this question is it is discontinuous, or no, it is not continuous. at x equals -4. So, question, little side note. What about at x equals 3, right here? Would this pass the continuity test?
No.
Does it exist at x equals 3? Yes. Does it approach the same number from both sides? Yes. Is the number it approaches from both sides the same as the number it is at that point? Yes. So it would be continuous at, say, this point, or in fact, any other point besides x equals -4. And just so you recall, for piecewise functions, let's say it was this, and then it did this weird parabola thing, and it wasn't this guy down here. This would be a continuous function, even though it's two types of graphs, if they were connected at the joints of the piecewise function. So just so you're aware, kind of some other things to be aware of. So thank you for watching, Internet friends. Have a great day. Bye-bye. Oh, actually, this video is almost 11:11, and that would be good luck, so let's fill out these last few seconds. But of course, as a mathematician, I don't believe in luck. Bye.